Welcome to this coding walkthrough. Today, we're tackling LeetCode problem number 1801, number of orders in the backlog. This is an interesting problem that challenges our ability to efficiently manage and process orders using data structures. Let's dive in and explore the problem, understand its requirements, and walk through the solution step by step. In this problem, we are tasked with processing a series of orders represented as a 2D array called orders. Each order is represented by three values: price_i, amount_i, and order type_i. The price_i specifies the price associated with the order, the amount_i tells us the quantity of items in the order, and the order type_i determines whether it is a buy order or a sell order. A value of 0 for order type_i indicates a buy order, while 1 represents a sell order. Buy orders aim to purchase items at the specified price or lower, while sell orders aim to sell items at the specified price or higher. If both orders have the same item count, they completely cancel each other out. Any unmatched orders are added to a backlog, which holds orders awaiting fulfillment. The goal is to determine the total number of items remaining in the backlog once all orders have been processed. Whenever a buy order and a sell order satisfy these conditions, they match, and the smaller order is fully processed, reducing the item count of the larger order. Because the number of items in the backlog can grow very large, the problem requires us to return the result modulo 10 to the power of 9 plus 7. Looking at the structure of the input, the orders array contains at most 10 to the power of 5 rows, with each row consisting of 3 elements: price_i, amount_i, and order type_i. The constraints specify that price_i and amount_i can be as large as 10 to the power of 9, meaning the problem involves handling very large values efficiently. For the output, we need to calculate the total number of items remaining in the backlog after all orders have been processed and return this value modulo 10 to the power of 9 plus 7. The examples provided will help illustrate how to process these orders and manage the backlog. Let's consider the first example to understand the process. The input array orders contains 4 orders: 10, 5, 0, 15, 2, 1, 25, 1, 1, and 30, 4, 0. The first order, 10, 5, 0, is a buy order for 5 items at a price of 10 or lower. Since there are no sell orders in the backlog yet, this order is added to the buy orders backlog. The second order, 15, 2, 1, is a sell order for 2 items at a price of 15 or higher. This sell order cannot match the existing buy order in the backlog because its price of 15 is greater than 10, so it is added to the sell orders backlog. Next, we process the third order, 25, 1, 1, which is another sell order. Similar to the previous sell order, it cannot match any buy orders in the backlog and is therefore added to the sell orders queue. Finally, the fourth order, 30, 4, 0, is a buy order for 4 items at a price of 30 or lower. This buy order can match the sell orders in the backlog sequentially, starting with the order, 15, 2, 1. When the buy order, 30, 4, 0, matches the sell order, 15, 2, 1, 2 items are matched, which fully satisfies the sell order and reduces the buy order to 30, 2, 0. The sell order, 15, 2, 1, is removed from the backlog. Next, the reduced buy order, 30, 2, 0, matches the sell order, 25, 1, 1, resulting in 1 item being matched. This fully satisfies the sell order, 25, 1, 1, leaving the buy order with 1 item remaining, represented as 30, 1, 0. After processing all possible matches, the remaining buy order, 30, 1, 0, is added to the backlog. At this point, the buy orders backlog contains 10, 5, and 30, 1, while the sell orders backlog is empty. The total number of items in the backlog is the sum of the amounts in the buy orders, which is 5 plus 1 equals 6. This is the output for this example. In the second example, the input contains 4 orders: 7, 1 billion, 1, 15, 3, 0, 5, 999999997, 0, and 5, 1, 1. The first order is a sell order for 1 billion items at a price of 7 or higher. Since there are no buy orders in the backlog, this sell order is added to the sell orders queue. The second order is a buy order for 3 items at a price of 15 or lower. It matches with the first sell order because 15 is greater than or equal to 7. 3 items are matched, which fully satisfies the buy order and reduces the sell order to 7,999999997,1. The third order is a buy order for 999,999,997 items at a price of 5 or lower. Since its price of 5 is less than 7, it cannot match the sell order and is added to the buy order's backlog. Finally, the fourth order is a sell order for one item at a price of 5 or higher. It cannot match the existing buy order because its price of 5 does not satisfy the condition for the buy order. This sell order is added to the sell orders queue. The total number of items in the backlog is the sum of all unmatched buy and sell orders modulo 10 to the power of 9 plus 7, which results in 999,999,984. To summarize, the problem comes with constraints that require efficient handling of up to 10 to the power of 5 orders, each with potentially large values for price and amount. This calls for the use of priority queues to manage the buy and sell orders in the backlog efficiently. Priority queues allow us to quickly access the highest priority orders for matching, whether they are the highest priced buy orders or the lowest priced sell orders. Additionally, we must be careful with modulo operations to ensure that the result fits within the specified range, especially when dealing with very large numbers. Edge cases to consider include scenarios where the backlog is initially empty, where orders have extremely large values, and where the number of orders is at the upper limit of the constraints. To solve the problem of determining the number of orders in the backlog, we need to efficiently manage and process buy and sell orders. The most straightforward way to approach this is the brute force method. Here, we iterate through the list of orders and use nested loops to manually search for matches in the backlog. A match occurs when a buy order can purchase from a sell order at a price equal to or less than the buy price, or when a sell order finds a buy order willing to pay a price equal to or greater than the sell price. While this approach is easy to implement and intuitive, it's computationally expensive. The nested loops result in a time complexity of n squared, which becomes impractical for large inputs, especially when the number of orders reaches the upper constraints defined in the problem. This inefficiency highlights the need for a more optimized solution. Now, to address the inefficiency of the brute force approach, we use an optimized strategy that leverages heaps. Two priority queues are introduced, a max heap for buy orders and a min heap for sell orders. Using these heaps allows us to efficiently retrieve the most relevant orders for matching. Specifically, for a buy order, we check the top of the sell heap to see if there's a sell order with a price that's less than or equal to the buy price. Similarly, for a sell order, we compare it with the top of the buy heap to determine if a match can be made at a price greater than or equal to the sell price. If no match exists, the order is added to the appropriate heap. This approach significantly improves efficiency, as inserting or removing from a heap takes log n, and processing all orders results in a time complexity of n log n. While heap management adds some complexity to the implementation, the performance boost makes this trade-off worthwhile. The optimized heap-based approach is the chosen strategy because it effectively balances efficiency and scalability. The key insight here is recognizing that prioritizing orders is essential for matching efficiently. Buy orders are processed by prioritizing higher prices, while sell orders prioritize lower prices. Heaps are an ideal data structure for this purpose, allowing us to dynamically insert and retrieve the most favorable orders. By avoiding the exhaustive comparisons of the brute force approach, we reduce the time complexity to n log n, making the algorithm suitable for handling up to 100,000 orders, as required by the problem constraints. While the implementation is more complex, the ability to process large inputs quickly and dynamically handle orders as they arrive makes this approach the best choice. To implement this strategy, we start by initializing two heaps, a max heap for buy orders and a min heap for sell orders. Then, we iterate through the list of orders. For each buy order, we attempt to match it with the lowest priced sell order in the sell heap. Similarly, for each sell order, we check for a match with the highest priced buy order in the buy heap. If a match is impossible, the order is added to its respective heap. Once all orders are processed, we calculate the total remaining orders in both heaps, applying the modulo operation with 10 to the power of 9 plus 7 as required by the problem. This approach ensures that we handle partial matches and large inputs effectively while maintaining efficiency throughout the process. In this problem, number of orders in the backlog, our task is to simulate a stock trading system where buy and sell orders are processed through a backlog. Orders can either be matched instantly, if there's a compatible order already in the backlog, or they remain in the backlog until a future match becomes possible. The ultimate goal is to determine how many orders are left in the backlog after all given orders have been processed. To begin, we need to understand the properties of an order. Each order has three key attributes: the price, which specifies the cost per unit of the order, the amount, which is the number of units in the order, and the type, where 0 indicates a buy order and 1 indicates a sell order. Now, the conditions for matching are straightforward. Buy orders can only match with sell orders if the sell price is less than or equal to the buy price, and sell orders can only match with buy orders if the buy price is greater than or equal to the sell price. These matching rules ensure that trades occur at mutually acceptable prices for both parties. To efficiently handle the matching and processing of orders, we need to carefully choose our data structures. For sell orders, we use a min heap, which allows us to quickly access the lowest price sell order. For buy orders, we use a max heap, enabling us to retrieve the highest price buy order efficiently. Heaps are ideal for this problem because they support constant time retrieval of the smallest or largest element and logarithmic time for insertion and removal. This efficiency is essential given the dynamic nature of order matching. Once our data structures are set up, we can process each order by following a systematic approach. First, we check if the incoming order can be matched with orders in the backlog. For a buy order, this means checking if the lowest sell price is less than or equal to the buy price. For a sell order, we look for the highest buy price that meets or exceeds the sell price. While a match is possible, we execute trades by deducting the matched amounts from both orders. If any portion of the incoming order remains unfulfilled, it is added to the appropriate heap, preserving the backlog for future matches. Finally, after all orders have been processed, the total remaining units in the buy and sell heaps give us the number of orders left in the backlog. Several key insights emerge from this approach. First, the matching logic ensures that trades only occur when there is price compatibility between buy and sell orders. This guarantees that both parties agree to the transaction. Second, the use of heaps significantly enhances efficiency by eliminating the need to scan through the entire backlog for each new order. This optimization reduces the time complexity, making the algorithm scalable for larger inputs. Additionally, there are critical edge cases to consider. For instance, orders with 0 units are ignored as they have no impact. When orders partially match, only the unmatched portion is added back to the backlog, ensuring accuracy. Finally, if no matching orders exist in the heaps, the incoming order is directly added to the backlog. For the data structures, the min heap for sell orders is organized by price in ascending order, with each entry representing the price and the amount of units available at that price. The max heap for buy orders works similarly but is sorted in descending order by price. These structures allow us to quickly identify and process the most relevant orders. Now, let's analyze the complexity of this algorithm. The time complexity is O, n asterisk log k, where n is the number of orders and k is the maximum size of the heaps. This comes from the fact that for each order, heap operations like insertion and removal take O, log k, time. The space complexity is O, k, which accounts for the memory used by the heaps. To illustrate how the algorithm works, let's walk through an example. Suppose the input orders are 10, 5, 0, 15, 2, 1, 25, 1, 1, 30, 4, 0. First, we process the buy order, 10, 5. Since there are no sell orders in the backlog, this order is added to the buy heap. Next, we process the sell order, 15, 2. There are no matching buy orders because 10 is less than 15, so this order is added to the sell heap. Then, we process the sell order, 25, 1. Again, no matching buy orders exist, so this order is added to the sell heap as well. Finally, we process the buy order, 30, 4. This order matches with the sell order, 15, 2, and the remaining, 32, matches with the sell order, 25, 1. After processing all the orders, the final backlog consists of a buy heap with one order, 10, 5, and a sell heap with one order, 25, 1. The total number of remaining orders is 6. To optimize further, we can use in-place heapify operations to reduce overhead during heap maintenance. Additionally, we can skip processing orders with 0 units to avoid unnecessary computations. These optimizations ensure that our solution remains efficient and scalable. By leveraging heaps and adhering to the matching logic, we effectively handle all edge cases and deliver a robust solution to the problem. Here, we start by importing the heap module, which is essential for working with heaps in Python. Then, we define a class named solution and implement the getNumberOfBacklogOrders method. Inside this method, we initialize a constant mod to handle the modulo operation later, as the problem requires results to be returned modulo 10 to the power of 9 plus 7. Next, we set up two heaps, cell_orders, which is a min heap to store cell orders, and by_orders, which is implemented as a max heap by inverting the price values. This inversion allows us to simulate max heap behavior since Python only provides min heaps by default. Now, we iterate over the list of orders. Each order contains three values: price, amount, and order_type. If the order_type is 0, it indicates a buy order. In this case, we attempt to match the buy order with the lowest priced cell orders in the backlog. Using a while loop, we check if there are cell orders available, and if the sell price is less than or equal to the buy price, we proceed with the transaction. We reduce the sell amount or buy amount accordingly and push any remaining sell orders back into the heap. If there's any unfulfilled buy amount left after processing all possible matches, we add it to the by_orders heap, using a negative price to maintain max heap behavior. If the order_type is 1, the order is a sell order. In this case, we attempt to match the sell order with the highest priced buy orders in the backlog. Using a similar while loop, we check if there are buy orders available and if the highest buy price is greater than or equal to the sell price. We then reduce the buy or sell amounts accordingly and push any remaining buy orders back into the heap. If there's any leftover sell amount after processing all possible matches, we add it to the cell_orders heap. Once all orders have been processed, we calculate the total number of orders remaining in the backlog. This is done by summing up the amounts from both the by_orders and cell_orders heaps. Finally, we return the total modulo mod to ensure the result meets the problem's constraints. This approach ensures that we efficiently manage the backlog and process orders while adhering to the requirements of the problem. Here, we start by defining the getNumberOfBacklogOrders method, which takes a 2D array of orders as input. We declare a constant mod to handle large numbers, as the result must be returned modulo 10 to the power of 9 plus 7. Next, we set up two priority queues, cell orders as a min heap based on price, and buy orders as a max heap. In Java, we achieve the max heap behavior for buy orders by using a comparator that compares prices in descending order. Then, we loop through each order in the input. Every order is defined by three values: price, amount, and order type. If the order type is 0, it represents a buy order. In this case, we try to match it with the lowest priced cell orders in the cell orders queue. As long as there are cell orders with prices less than or equal to the current buy order price, and the buy order still has remaining quantity, we process the matches. If the cell order has more quantity than the buy order, we reduce its quantity and push it back into the heap. Otherwise, we fully consume the cell order, reducing the buy order's quantity accordingly. If, after attempting to match with cell orders, the buy order still has remaining quantity, we add it to the buy orders heap. Now, when the order type is 1, it indicates a sell order. The logic here is symmetric to the buy order case. We try to match the sell order with the highest priced buy orders in the buy orders heap. While there are buy orders with prices greater than or equal to the current sell order price, and the sell order still has remaining quantity, we process the transactions. If the buy order has more quantity than the sell order, we reduce the buy order's quantity and reinsert it into the heap. Otherwise, we consume the buy order completely and decrease the sell order's quantity. If the sell order still has some unfulfilled quantity after the matching process, we add it to the sell orders heap. At this point, all the orders have been processed, and we calculate the total number of unfulfilled orders remaining in both heaps. We iterate through the buy orders heap and sum up the quantities, taking modulo mod after each addition. Finally, we perform the same summation for the cell orders heap, adding their quantities to the total while applying modulo mod to ensure the result stays within bounds. Once all orders are accounted for, we cast the total orders value to an integer and return it as the result. This completes our method, ensuring that we process all orders efficiently while maintaining the rules of buy and sell order matching. The use of priority queues allows us to dynamically manage and prioritize orders based on their price, making this approach both time-efficient and straightforward to implement. In this problem, we are tasked with determining the number of unprocessed orders left in the backlog after processing a series of buy and sell orders. Each order is defined by three components: the price, the number of units, and the order type, where 0 represents a buy order and 1 represents a sell order. To manage this, we use two heaps, a max heap for buy orders, which we implement by storing negative prices, and a min heap for sell orders. The idea is to match orders based on price compatibility. If a match occurs, the corresponding units are processed, and any remaining unprocessed units are added back to the backlog. For example, let's consider the input 10, 5, 0, 15, 2, 1, 10, 1, 1. In this case, we'll show how orders are processed step by step, updating the heaps as we go. Initially, both the buy heap and the sell heap are empty. The first order, 10, 5, 0, is a buy order for 5 units at a price of 10. Since there are no sell orders in the backlog to match this buy order, it is added directly to the buy heap, which now contains -10, 5. Next, we process the second order, 15, 2, 1, which is a sell order for 2 units at a price of 15. The buy heap has orders, but the prices are incompatible since 15 is greater than 10. Therefore, this sell order is added to the sell heap, resulting in 15, 2. Finally, we process the third order, 10, 1, 1, which is a sell order for 1 unit at a price of 10. This price matches an existing buy order in the heap, so the order is partially executed. 1 unit is processed, reducing the buy heap to -10, 4, and the sell order is fully matched, leaving the sell heap unchanged. At the end of these operations, the total orders in the backlog are 4 units in the buy heap and 2 in the sell heap, for a total of 6. The output for this example is 6, which represents the total number of unprocessed orders in the backlog after processing all the orders. Now, let's analyze another example where the orders partially match. Consider the input 7, 5, 0, 6, 2, 1, 8, 3, 0. Again, we will process each order step by step, updating the buy and sell heaps as necessary. Initially, both heaps are empty. The first order, 7, 5, 0, is a buy order for 5 units at a price of 7. Since there are no sell orders to match, this order is added to the buy heap, resulting in -7, 5. Next, we process the second order, 6, 2, 1, which is a sell order for 2 units at a price of 6. This price is compatible with the existing buy order in the heap, so the order is partially executed. 2 units are processed, reducing the buy heap to -7, 3, and the sell order is fully matched. Finally, the third order, 8, 3, 0, is a buy order for 3 units at a price of 8. Since there are no sell orders to match, this order is added to the buy heap as well, resulting in -8, 3, -7, 3. At the end of these operations, the total orders in the backlog are 6, with 3 units at price 8 and 3 units at price 7. The output for this example is also 6. Now, let's consider a simpler case where all orders fully match. The input here is 5, 3, 1, 5, 3, 0. We will again process these orders step by step. Initially, both heaps are empty. The first order, 5, 3, 1, is a sell order for 3 units at a price of 5. Since there are no buy orders to match, this order is added to the sell heap, resulting in 5, 3. The second order, 5, 3, 0, is a buy order for 3 units at a price of 5. This price matches an existing sell order in the heap, so the order is fully executed. 3 units are processed, and both the buy and sell heaps are emptied. At the end of these operations, there are no unprocessed orders left in the backlog. The final state shows that both the buy heap and the sell heap are empty, meaning there are no orders remaining in the backlog. The output for this example is 0. These examples highlight how the matching process works using heaps, ensuring that orders are processed efficiently while unprocessed orders are tracked accurately in the backlog. To analyze the time complexity of our solution, we need to break it down into its key components, processing each order, performing heap operations, and summing the remaining orders at the end. First, each order in the input list is processed by either attempting to match it with orders in the opposing heap or, if matching is not possible, adding it to the appropriate heap. If we let n represent the total number of orders, this means we'll process n orders in total. Next, heap operations are central to the solution, particularly heap pop and heap push, which allow us to remove and insert orders efficiently. Both of these operations have a time complexity of O log k, where k is the current size of the heap. Importantly, while it might seem like an order could interact with every other order in the opposing heap, orders are removed from the heap once matched, which ensures that the total number of heap operations remains proportional to n. Finally, when summing the remaining orders at the end, we iterate through the heaps. Since the total number of orders left in both heaps is at most n, this step contributes an additional O, n, to the time complexity. When we combine all these components, the overall time complexity is dominated by the heap operations. Processing all orders involves O, n asterisk log n, time due to the logarithmic cost of each heap operation applied n times. The summation step, which is O, n, is comparatively smaller and does not change the overall complexity. Therefore, the total time complexity of the solution is O, n asterisk log n. Now, moving on to space complexity, the primary factor here is the storage of the heaps. We use two heaps, one for by orders and one for cell orders. In the worst-case scenario, if no orders are matched, all n orders could remain in the heaps. Since each order is stored as a tuple of price and amount, the space required for each order is O, 1. This means the total space required for the heaps is O, n. Additionally, we have a few variables like mod, price, amount, and temporary variables for heap operations, but these require only O, 1, additional space. As a result, the space complexity is dominated by the heaps and is O, n. To summarize, the overall space complexity of our solution is O, n. This is primarily due to the space needed to store the orders in the two heaps. Now, let's compare this heap-based approach to a brute force method. In a brute force approach, for every new order, we would iterate through all unmatched orders in the backlog to find possible matches. This would result in a time complexity of O, n squared, in the worst case, as each order could require comparisons with all previous unmatched orders. By contrast, the heap-based approach improves efficiency significantly. Heaps allow us to retrieve the best matching order, either the minimum for cell orders or the maximum for by orders, in O log n time, rather than O, n. This optimization reduces the time complexity from O, n squared, to O, n asterisk log n, making the heap-based approach far more scalable for large inputs. Now, let's analyze the performance of this solution across best, average, and worst-case scenarios. In the best case, every order is immediately matched with an opposing order. This means the heaps remain empty, and processing each order only involves a minimal heap operation with a cost of O log 1, which is O, 1. Thus, the total time complexity in the best case is O, n. In the average case, some orders are matched while others remain in the heaps. The average case time complexity remains O, n asterisk log n, because the logarithmic cost of heap operations still applies as we process the orders. In the worst case, no orders are matched. This means all n orders remain in the heaps, and each heap operation continues to cost O log k, where k is the size of the heap. Even in this scenario, the overall time complexity remains O, n asterisk log n. Finally, let's justify the O, n asterisk log n, complexity mathematically. Each order involves a constant number of heap operations, typically a push and possibly a pop, each of which takes O log k time, where k is the current size of the heap. Over n orders, the total cost of these operations accumulates to O, n asterisk log n. While we also sum the remaining orders at the end, this step is O, n, which is asymptotically smaller than the heap operations and does not affect the overall complexity. Therefore, the dominant factor is the cumulative cost of heap operations, and the overall time complexity is O, n asterisk log n. When working on this problem, there are several common mistakes to watch out for. One of the most frequent is confusing the logic for matching buy and sell orders. Remember, a buy order will match when the buy price is greater than or equal to the sell price, while a sell order matches when the sell price is less than or equal to the buy price. Mixing these conditions up can result in entirely incorrect outcomes. Another pitfall involves using inefficient data structures. For example, relying on a standard list instead of a priority queue to manage the backlog can lead to slower operations, especially as the number of orders grows. Priority queues, or heaps, are designed to handle insertion and removal in logarithmic time, making them far more efficient. Additionally, you need to be mindful of the problem's constraints, where the number of orders can go up to 100,000. If your solution isn't optimized, you risk running into time-limit-exceeded errors. Finally, it's crucial to correctly handle the leftover orders in the backlog after processing matches. Ensure the quantities are updated accurately so that no orders are mishandled or skipped during the process. Another area to be cautious about is the modulo operation, as the problem often specifies returning the result modulo 10 to the power of 9 plus 7. Forgetting to apply the modulo, or applying it incorrectly, such as before summing up quantities instead of after, can lead to wrong answers. From an interview perspective, this problem is an excellent opportunity to demonstrate your ability to recognize patterns. Specifically, it falls under the category of order processing or heap-based matching problems, so highlight your understanding of when and why to use priority queues for efficient operations. Be ready to discuss trade-offs, such as how a priority queue improves the time complexity from O(n squared, with a brute force approach to O(n log n). Interviewers may also test your handling of edge cases, like scenarios where all orders are buy orders or sell orders, or cases with identical prices but varying quantities. Lastly, it's a great chance to connect the problem to real-world systems, such as stock exchanges or online marketplaces, where similar algorithms are used for matching transactions. This problem also shares similarities with several other LeetCode problems, making it a great opportunity to deepen your understanding of related concepts. For example, LeetCode 295, Find Median from DataStream, demonstrates the use of two heaps to maintain order statistics dynamically. LeetCode 703, KTH largest element in a stream, focuses on efficiently retrieving the KTH largest element using a heap. Another related problem is LeetCode 23, Merge K-sorted lists, which uses heaps to merge multiple sorted lists efficiently, a technique that parallels how we manage the buy and sell orders here. Finally, LeetCode 621, Task Scheduler, involves a similar use of priority queues to handle tasks efficiently while satisfying certain constraints. By exploring these problems, you can strengthen your grasp of heap-based algorithms and their diverse applications. When considering alternative approaches to solve this problem, there are three main strategies to evaluate. The first is the brute force approach, where you directly iterate through the backlog to find matching orders. While this method is straightforward to implement, it becomes inefficient for large inputs due to its O(n squared) time complexity. The trade-off here is simplicity of implementation versus poor scalability. The second approach, and the optimal one, is using priority queues. By employing a max heap for buy orders and a min heap for sell orders, you can efficiently match and insert orders with a time complexity of O(n log n). This approach is both fast and manageable, though it does require familiarity with heap operations. Lastly, there's the balanced binary search tree approach, such as using an AVL tree. This method can also achieve efficient matching, but it's less common in practice due to its higher implementation complexity. The trade-off here lies in achieving similar efficiency to heaps but with added complexity in managing the data structure. Each approach has its place, but the priority queue method is generally the most practical for this problem. Great job! To summarize, we tackled the number of orders in the backlog problem by leveraging priority queues for efficient order processing. We explored the time and space complexities and discussed key takeaways, such as the importance of data structures for real-world scenarios. Thanks for watching, and be sure to like and subscribe for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!